Log on, tune in, find out. Another good idea from Cambridge.
Dabholkar, who will tell us about localization and exact quantum computing.
Okay, so let me begin by thanking the organizers for inviting me to give this talk. I'll tell you about some recent results in using localization to understand the exact quantum entropy of black holes. And the plan of my talk is I basically I'll first describe the motivation, what is quantum entropy in the context of ADS2 holography. Then I'll describe how localization can be used to compute this, and I'll give the microscopic counting of some simple example so that you have something to focus on. And then I will describe some of the calculations. I realize this is the last talk of the conference. You're all tired, but this will be a slightly heavy which I will rush through quickly, I promise. And then I will describe how to lift this supergravity computation to string theory, and then I'll end with some conclusions. This is based on work done with my student João and Samir, who is here, and João actually will be here starting next year in Cambridge. And if I get if I have time, also some earlier work with Ashok, and if there is time, I will briefly describe some results in this new paper that is about to come. But I'll mostly be talking about these two papers. So there are two related motivations. I don't need to repeat this, but the entropy of black holes remains one of the most important and precise clues about the microstructure of quantum gravity. So the question is, can we compute exact quantum entropy of black holes, including all corrections? So in fact, as you know, even defining quantum entropy is actually a bit tricky. For example, the Wald entropy, as I will describe, is not quite adequate for these purposes. So first one need to have a definition of a quantum entropy, and then find some method of computing it. Related, of course, as we understand now, that near horizon BPS black holes would give rise to holography, which has emerged as one of the central concepts in understanding quantum gravity. So this motivation also sort of flows into trying to find simple examples of ADS CFT holography, where one can actually try to do it at the quantum level rather than at the semi-classical level, and maybe even prove it. Okay, so let me just state the problem. So basically, the BPS black hole, as we know, is this famous area upon 4, and Strominger and Waffa showed that it agrees nicely with large log of the degeneracy of the corresponding states for large charges, and this matches beautifully. But clearly, there would be corrections of order 1 upon q, and this raises two important questions. I mean, is there an exact formula to which this is an approximation? If you get some formula in physics, you should ask, how do you compute corrections in a systematic way? So can we compute these corrections in a systematic way on both sides? And these finite size effects are actually quite interesting, because unlike the area formula, which is completely universal, which just follows from the Einstein-Hilbert action, these finite size effects actually depend in the details of the theory, and therefore they are in a way more interesting, because one can there is a general universal, since we don't know which phase of string theory might correspond to the real world, it's a useful strategy to focus on some universal criteria or universal properties that should hold in all phases of the theory, whether it's n equal to 4 compactification or some other compactification. And one such universal requirement of quantum gravity is that in any phase of the theory that admits a black hole, one should be able to interpret the black hole as a statistical ensembles of states. And this implies a very stringent requirement, much more stringent than just the area formula, that even the finite size corrections to the entropy, unlike the leading area formula, which depend on the details of the phase, should agree and should allow you to interpret the black hole as a statistical ensemble. So, since we are quite far off from finding the phase of the theory which describes LHC, we could benefit by focusing on some features which should be true in any phase, and then work in some phase where we can actually do the computations. Conversely, we can use the knowledge of exact black hole results to learn about the exact non-perturbative spectrum, and this has already been used. For example, if there is any putative counting formula, then one can check whether the black hole entropy agrees with or not. And this has already been used very successfully in the quarter BPS dione case. There were number of subtleties having to do with arithmetic duality invariance or the wall crossing, on which the counting formula should depend, and you could fix it partly by looking at the black hole. So, all of us know that there is a generalization of the Bekenstein-Hawking formula due to Wald, and it is a very nice generalization done in the 90s, completely for the reasons of a general relativist, nothing to do with string theory, and it basically can incorporate, it is a general machine that gives you corrections to Bekenstein-Hawking entropy for any local higher derivative effective action. So, as you know, the Bekenstein-Hawking formula, this follows basically you start with any local action with r plus r square and so on, and then demand first law of thermodynamics, and that gives you a definition of the entropy, that is the Wald entropy. Now, therefore, because it uses a local action, it does not include quantum effects that would come from integrating over massless fields, and these are actually in general essential, as we will see, for example, for duality invariance. So, you cannot just drop the effects of a local action can incorporate effects coming from integrating over massive fields, but if massless fields are going to make contribution, then you need some appropriate generalization of Wald entropy, and that is what I mean by the quantum entropy. And for a systematic comparison between the microscopic degeneracy with some notion of a black hole. So, microscopic degeneracy is of course clearly well defined, is the degeneracy of the number of states is in some Hilbert space, but you need some generalization of the quantum entropy, and that was proposed quite recently, a couple of years ago, by Ashok, using essentially ADS2 CFT holography, basically as a generalization of the Wald entropy. And the prescription is quite simple in the end. The details are, I will require another lecture to really go through, but in the end it is some functional integral over ADS2 of a Wilson line inserted at the boundary. So, ADS2, remember, is just a disk Euclidean ADS2, and as usual in ADS you need to put some cutoff. Let us put a cutoff at r is equal to r naught, and with this cutoff you insert a Wilson line that circles this boundary of the disk, and then you perform a functional integral over all string fields, and this Wilson line insertion is essential so that the classical variational problem is well defined, because there are some boundary terms when you do the variation of the Maxwell action, and to cancel those you need this boundary term. So, that is like just to make the functional integral well defined. Now, the black hole correspondingly, so this allows you to define some kind of a partition function which we can call Z ADS2, which depends on the charges of the original black hole that it started with, and Sen showed that this actually for large charges can be approximated by exponential of the Wald entropy. And this should therefore correspond to the total number of states of the black hole. Now, let me just very quickly go through some details. Basically, asymptotically what you want when you say you want to do functional integral, that means that you want to only have asymptotic ADS2 space, and over here you want to allow all sorts of quantum fluctuations, both for all the fields including the metric and the gauge fields and the scalar fields. So, asymptotically they should go over to the ADS2 space, asymptotically the scalar field should go to the attractor values, the the constant values that they acquire that depend on, so asymptotically the scalar fields phi will go to some UA which depends on the attractor values which depend on the charges, and similarly for the gauge field. But over here they can fluctuate arbitrarily and you just have to do the functional integral.
You said this boundary term in the gauge field is needed because of to cancel some boundary terms from these fluctuations, right?
Yeah.
But is it obvious that no term in gravity, I mean no term for
Yeah,
the gravitational boundary?
It's, I mean, yeah, it's not necessary. So
Not
this,
necessary.
not necessary.
And that's of
It's probably obvious if you, yeah.
I was just wondering what feature of the gauge theory sector is it something to do with magnetic charges, or
No, I think
actually
it's just
this expression, does it depend on electric or magnetic? I mean,
no, the magnetic charges are just so typically you will have ADS2 cross S2, and the magnetic charges are just fluxes through the S2. But you can do kind of a dimensional reduction and regard the magnetic charges as some numbers that are given that specify your compactification. So this is a prescription, and of course this functional integral is infrared divergent as we know because of the large volume divergence of ADS2, and that's why we have a regulator. So basically you need a prescription to cut it off and regularize it and then remove the divergence, and that's usually what is sort of goes under the name of holographic renormalization. But here is the prescription is very simple. You put a cutoff at large radius. The bulk Lagrangian is a local functional, so you can argue that this is it has this form, and basically it will depend on this will be a functional, all these constants will be functionals of the various gauge fields that are fluctuating that you want to integrate over. But the main point is that you want to subtract out this divergent piece and then take the limit R naught going to infinity. So that's the holographic renormalization, and therefore the S bulk is the C1 as a functional of these various fields.
I think the answer is that it's because you're in the microcanonical ensemble. That's what tells you that you need this integral A.
with respect to the electric charge.
That's right.
That's right, okay. Because there is no charge corresponding to the, okay. Now this quantum entropy, therefore, this allows you to define a notion of a quantum entropy rather than just talking about wall entropy. Now what you should really do is compute this Z ADS2 gamma. And clearly, because you're doing a functional integral, it includes automatically integration over massless fields, and this is essential for duality invariance and for a systematic comparison. And as I will show you, these non-local effects are actually quite important, and they make a big difference to the answer. So to summarize, the most ambitious goal is to compute D of QP from some boundary dynamics of branes, and this W of QP, okay, I call this Z, but I call it W here because it's a Wilson line from the bulk for some arbitrary finite charges without taking large charge limit, and check if the two agree. Now, so basically we need to compute both D of gamma and W ADS2, and most of my talk will be about the left hand side. But the right hand side also has been solved, and it's actually a lot of work by various people. But we now know the exact spectrum of both half and quarter BPS diionic black holes for all charges at all points in the moduli space of certain n equal to 4 theories, and for a large class of states in n equal to 8 theories. And this is a bunch of people who have done that. So I'm just going to take these results, but actually in fact I'm going to only focus on n equal to 8 in this talk. And for n equal to 8, the answer is extremely simple. You just have this function, the exact macroscopic degeneracies of 1/8 BPS. So these are large black holes with large horizon compared to the string scale. These are 1/8 BPS diionic black holes with some charge vector q and p, and they are given in terms of the Fourier coefficients of this counting function. And the theta function has the usual product, and you have the eta function which has the usual product. So it's you can just put it on a computer and calculate the degeneracies for any given charge. This is of course not the most general. There are issues about the arithmetic duality invariance, but I will not go into it. So you can just take some configuration which which is described by this counting function, and then you know the degeneracies. But of course, doing it on a computer is not very efficient, and as you know, there is this very nice random exact expansion of this counting, this Fourier coefficients, which is given by the Rademacher expansion, and which uses the modular properties of this function. So, because this function has modular properties, it's both modular and elliptic, meaning it's invariant under, essentially invariant under translations in Z. You can develop its Rademacher expansion, and it looks like that. It's the d of delta, which is delta is the U duality invariant q square p square minus q dot p, which is an integer. It admits an exact expansion as a sum from c going to 1 to infinity of d of c of this delta, with d of c of this delta is given very explicitly in terms of some standard function like the modified Bessel function I tilde 7 by 2, and very number theoretic sum which is called the Kloosterman sum. And the Kloosterman sum actually looks quite complicated. It depends on various integers. So, it is a very number theoretic object, and there is some deep number theory associated with it. So, if you are really ambitious, one would like to derive all these terms going from 1 to infinity from the microscopic gravity point of view, and that is sort of the goal. And I will describe the first term, and we do not yet understand the Kloosterman sum completely. So, our goal now will be to evaluate the formal. So, this is all very nice. This definition given by Sen is very nice, but it is kind of very formal, and what do you do with it? I mean, how can we evaluate a functional integral of string theory? String theory meaning integrating over all string fields in space time, not the world sheet string theory, on this ADS2 space. So, this is very non-trivial, and you might even think that you are being too ambitious. But surprisingly, one can actually go quite far using localization techniques, and you can reduce this functional integral to a finite number of ordinary integrals. And with enough supersymmetry, it seems possible to even evaluate these ordinary integrals all the way under certain assumptions about the normalizations that I will talk about. And so, the bulk of my talk will be about some recent progress in this evaluation. And those of you who might be familiar with some gauge theory computations, I just want to give you, some of you might have seen this very nice computation by Pestun of a Wilson line on S4. So, if you take an S4 and put a Wilson line here, then you can actually show that S4 with a line removed is conformally equivalent to ADS2 process 2. And the Wilson line computation therefore, and the Wilson line is inserted in the boundary of this ADS2. So, the Wilson line computation in the gauge theory has a number of formal similarities with the computation that I want to do. But of course, that computation was done in the boundary Yang-Mills theory, whereas here we are doing the computation in the bulk and where gravity is present. So, it is a generalization of localization techniques to in the gravitational context. And to my knowledge, this is probably the first time these methods have been used to a supergravity theory. So, now let me briefly tell you what is localization if you have not been spending your time in supersymmetric field theories. The basic idea is that the fact that the Grassmann integration gives you 0. So, if you are doing some functional integral which has a exact fermionic symmetry, then you can sort of use a Faddeev-Popov procedure to divide the field space in terms of orbits of this fermionic symmetry and take out the volume of this supergroup outside, and since the supergroup volume is 0, your functional integral will be just 0. But if this fermionic symmetry acts with fixed points instead of acting freely, then of course you will pick up contributions from the fixed points of this symmetry. So, that is the idea. So, therefore, the functional integral will localize onto the fixed points of this fermionic symmetry. So, that is the idea of localization, and that is what the word localization means. And to implement it, you can do it more formally. What you do is, so basically what you want to do some functional integral like this on a supermanifold, which is the supermanifold is a space of all fields, you have some Wilson line insertion, you have some supersymmetric action. You also need to make the Wilson line supersymmetric, as for example Maldacena did for the Wilson line, and you have a supersymmetric measure, and therefore you are evaluating some q invariant function with a q invariant measure. To do that, you deform this by adding to it some lambda qv action, where q square is some fermionic vector field which generates this symmetry, which squares to a bosonic field for a compact bosonic field, and v is a fermionic H invariant function. So, it is easy to see that you can just differentiate d by lambda, it will pull down some qv, and then using the fact that everything is q invariant, you can show that the derivative is 0, and therefore I of lambda is independent of lambda. So, therefore, instead of evaluating at lambda equal to 0, which is what you want to do, you can evaluate at lambda equal to infinity, and at lambda equal to infinity you can basically drop this term to leading order, and the semi-classical approximation of 1 upon lambda becomes exact, and that is the way you can, therefore semi-classical computations will give you exact answers. So, you have to do sort of make some clever choices of this, what is this qv, and if you do things well, then you will end up with something that you can manage. So, the choice of the supercharge. So, therefore, in this limit the functional integral will localize onto the critical points of this functional qv, and it will reduce the functional integral over field space to this localizing manifold. That is the basic idea. So, to apply to your our problem, we will pick q which squares to 4L minus j, where L generates, we have ADS2 cross S2, and L generates the rotations of the ADS2 disk, and then you pick some the J3 that is on the S2, which generates rotations on the S2. So, you pick this particular supercharge, and V you choose to be q times psi, where psi are all the fields in the theory, and then you are all set. You have SQ is equal to QV, V is given by this functional, and Q is given by this requirement that Q squares to L minus J. Now, to apply this directly in string theory, of course, is not feasible given the state of string field theory. So, we have to solve this problem in some simpler context, and this is what I am going to do now. So, I will just first solve this problem in supergravity. This you can think of this like a lemma, which is completely independent of my motivations from counting and etc. Just as a exercise in a functional integral in supergravity. So, imagine instead of W, a W hat QP, which is the same functional integral, but just over supergravity coupled to NV plus 1 vector multiplets. This is still a complicated functional integral over space-time fields, and I am going to show that how this particular complicated functional integral localizes. So, that is actually one of the main results, and then one has to put in additional information to really lift it to string theory with some additional assumptions that still need to be analyzed more fully. So, but this is already a huge simplification, that some complicated functional integral over supergravity fields is reduces to a finite dimensional ordinary integral over NV plus 1 real parameters. So, how does this work? Well, even to proceed, it actually is very essential to use off-shell formulation of supergravity. So, until now I was kind of innocently unaware of off-shell formulations in supergravity because it looks awfully complicated, but now you sort of develop an appreciation for this whole enterprise, because it allows you to do quantum, even it is not just some classical question of that the equations, when the symmetry algebra closes without using equations of motion, but it really is essential for doing quantum computations, as we will see. So, for n equal to 2 supergravity coupled to vector multiplets, a very nice off-shell formulation exists, and the multiplet structure is very simple. You have the gravity multiplet, which has the usual metric etc., and the gravitini, and then there is a vector multiplet, and the vector multiplet has a vector, a complex scalar, and some bunch of auxiliary fields and the fermions. There is an SU2R symmetry, so everything is I is the doublet index of the SU2, and the off-shell transformation, for example, looks like this. So, it is some derivatives of the x field etc., and the auxiliary fields appear here in an important way. Now, the importance of being off-shell is that the beauty of the off-shell supergravity is that you need to specify the supersymmetry transformations once and for all, and they don't depend on the choice of your action. So this is very much like for bosonic actions, you specify that the metric under coordinate transformation has this particular transformation property, it transforms as a tensor, and once you specify that, you don't need to keep modifying this transformation law of the metric if you add r square term or r to the 4 term. It's just group theory, and that's exactly what is achieved by this offshore formulation of supergravity, that you specify your symmetry laws in the beginning, and they are completely independent of any equations of motion, and then you can write down whatever action you want. And therefore, this will allow us to split this complicated problem in 2 steps, that we will first find kind of a universal localizing instantons using this offshore formulation, independent of which is valid for any physical action, and then we will put in the physical action and do this renormalization procedure. So this gives you a very nice clean separation for this computation. Moreover, as we will see, the auxiliary fields will turn out which are normally just eliminated from the physical action by just eliminated, they will acquire non-trivial position dependence and for this instanton solutions. So with this setup, we just have to calculate everything, and let's just look at the bosonic part. The bosonic part looks like this: q of omega for the QV action is the sum of perfect squares. It turns out that that this QV action is sum of perfect squares. So you can set each of these terms to 0 to get a first order differential equations, a set of first order differential equations, and it turns out that you can actually solve them exactly and get an exact answer, exact analytic solution. So this cube psi or q omega action looks like this. It's some complicated mess where you sort of so we have all these fields xi. So what I have done there is that you parameterize this xi as the value of the field at infinity, because at the infinity of the ADS2 it has to go to the attractor value, and then you define some fields hi or ji. So all these fields h and k and j are basically similarly for the y field yij. So h, j and k are basically the difference between the asymptotic values of the x field and the y field compared to their boundary values. So basically k, h and j are nothing but x and y. Okay, so that's what you should keep in mind, and they depend on the coordinates of the ADS2. Yeah, so this also has been done subsequently by my student João in unpublished work, and he has shown that they don't get excited.
They don't get what?
The fields in the wild multiplet remain. They are not excited.
Okay.
Okay, so this is some bunch of equations which you have to. So you set this equation to 0. These are all derivatives, so it will give you some first order differential equations which you have to solve, and it turns out you can solve them, and the final answer is very simple. The final answer is as follows: that the x fields basically asymptote to their attractor values at infinity of the boundary. So r. So let me now write down maybe the metric so that you know what r coordinate I am talking about. So I am using the ADS2 metric, which is of the form dr square 1 minus r square plus d theta square. So r goes from 1 to infinity, and r is equal to infinity is the boundary, and r is equal to 1 is the center of ADS2. So in those coordinates, this is the solution. So what does it mean? That the x field asymptotes to x star, but it has a non-trivial dependence as a function of r. So at the center it picks up some maximal value, which is parameterized by a real constant. Interestingly, the auxiliary field also has this profile and also has a maximal value at the origin, but the gauge fields don't move away from their attractor values. So therefore, this solves a major piece of the problem by identifying the offset field configurations onto which the functional integral localizes. And therefore, this reduces your functional integral to a finite dimensional integral over this C, which you can think of as the moduli of this instanton solution. So you have to basically figure out now, your problem is reduced to working on this moduli space of these instantons, and this instanton is universal and does not depend on the physical action. The scalar fields move away from the attractor values x star inside the ADS2, and this is quite interesting because you might think that the attractor mechanism was sort of required for supersymmetry. So if the scalar field is moving away from here, and they, because of that, they were at the minimum of some quantum entropy, some classical entropy function. So there is some classical entropy function as a function of these x fields, and x is equal to x star was the minimum of that function, so that the equations of motion of x were satisfied. Now here you manage to move away from it. As you're coming inside, the x fields are going away very far off shell because C can go to infinity. So therefore you can actually move very far away from the attractor values in the field space. So if the field space, if the attractor submanifold was something like that, you can go as far as you like from this attractor manifold, but still manage to maintain supersymmetry. And this is possible because somehow the y field gets excited in such a way that it holds this x field up there without spoiling the q supersymmetry. It doesn't preserve all the supersymmetries, but it preserves the q supersymmetry.
Aren't the equations you are solving conformal equivalent to equations on S4, and then you can just take conformal transformation?
Yeah, you could have done that. Yeah, so that's actually part of the reason we looked at your paper carefully. But the one complication is that you also have the x stars. So because of the fact you are working in supergravity and x star is not 0, actually you could going to the S4 doesn't necessarily simplify your life. I mean, you sort of trade one complication for another. But you can actually, you're right that this form could be guessed by going to the S4.
Let me answer the question another way. If you make conformal transformation to S4, what is the solution?
It's something simple. I think it's what you had found.
It's just constant.
Yeah, it's constant. Yeah, it's constant, exactly. But the point is that, okay, the thing is that if x star was not present, you could do that conformal transformation. But under the conformal transformation, x star changes. So what happens is on the S4, this part is constant, but this part is varying in R. So, you know, you have to, it doesn't help you, I mean, it sort of helps you to guess the answer, but you have to sort of do it all in one frame and then be sure that you have a solution. Okay. So anyway, are there any questions before I flash any more scary transparencies? Okay. So this is the only scary transparency. So now you have done, so therefore you have solved part of the problem. You have found these solutions as notice that these are part of the solutions are exactly similar to the solution that he had found in a gauge theory context, in a completely different context. But now to apply this to gravity, the nice thing in Yang-Mills theory, for example, was that the action was simple, it was just f square. But now we can no longer hide from the supergravity action, and we have to look at it, and we need to evaluate the physical action on the localizing instanton solution following the renormalization procedure outlined by that I outlined earlier, and we need to therefore figure out the renormalized action as a function of these instanton moduli C and the charges. And the action looks like this, very scary, and there are all kinds of auxiliary fields, and you have to substitute this solution and our solution x's and work out the procedure that we did. And substituting and localizing the instanton solution in this action, we can actually extract out a finite piece after removing the leading divergent piece. And after a tedious algebra, we obtain a remarkably simple form, and maybe there is a faster way of doing it by maybe using some manifestly superfield formulation in superspace. I mean, it suggests that I think there must be. So, and the final answer is very simple. It can be expressed as some script f phi q So these theories, gravity coupled to some number of vector multiplets, are specified by some superpotential, prepotential, which is a holomorphic, completely holomorphic function of these fields x, and given this prepotential, the script f is defined in this manner, where phi now are E star plus this 2IC, and this is very reminiscent of, very similar, identical to the topological string partition function that went into the OSV conjecture. So therefore, the S renormalized equals precisely the classical entropy function epsilon EQP. In particular, exponential of S renormalized is the topological string partition function, but the physics is quite different, because here, as we saw, we obtained this by a rather long procedure. First of all, this we are going very off shell from the attractor values, and this was justified by this localization techniques, and moreover, they are depending on the values of the scalar fields. Essentially, these phi's you can think of as the values of the scalar fields at the center of ADS2. So the phi's are basically the values of this, it's x star plus c is the value of the scalar field at the center of ADS2. So essentially, S renormalized is the prepotential evaluated, the imaginary part of the prepotential evaluated at the center of ADS2.
In the off-shell formulation of supergravity, I think you need one compensating
Yes.
micromultiplet
Yes.
as well.
Yes.
I can see that, but what does it localize on? If you
No, so that stays, that plays no role. I mean, it's 0 or whatever constant, whatever you had set it before. So that plays no role in this. Yeah, but there could be subtleties with the compensating vector multiplier that.
will you do higher derivatives as well at some point?
Well, in this talk I will not, but I think there could be possible subtleties with the compensating hypermultiplier, which, well, there could be subtleties, but there may not be subtleties also. Man. Okay. So this is what we obtain. Now now in the remaining 25 minutes, I'll just lift it to string theory and end with the conclusions. So basically, we lack a useful definition of string field theory to do such a functional integral, but we can proceed in 3 steps. We can imagine that we integrate out the massive string and Kaluza time modes to obtain a local Wilsonian effective action. Then you can solve this supergravity problem using this arbitrary local effective action, including all higher derivative terms, and then use these results that this lemma that I showed to evaluate W of QP. Now it turns out that in fact ADS2 admits ZC orbifolds labeled by an integer. So you might ask, where are all these other terms going to come from? WCQP. These are exponentially suppressed terms compared to c equal to 1, but they are present in our Rademacher expansion, as I will explain, which I showed you before. So where are we going to get this infinite sum over contributions? And that's actually comes out naturally in the ADS2 language, as shown by Sen and used also by Piolin and Murthy, that you can do orbifolds of this ADS2 by rotations. You can rotate by some ZC, Z3 for example in this case, and make a translation in some internal direction so that you have a well defined orbifold. And such configurations you can show actually by some coordinate transformation, actually because of some funny properties of ADS2, they asymptote to the same ADS2. Even though it looks like you are reducing the boundary by a factor of 3, you can make a coordinate transformation so that the boundary with the cutoff is basically the same. So you have to basically include all such configurations. Since you are doing a functional integral, you have to include all configurations which are the same boundary, and therefore these orbifolds also must be included in your functional integral. So that gives you a natural way how all the WC's will come, and it's also clear that their leading behavior. So anyway, so therefore we have at least an a priori way, a nice way of understanding all the terms that I showed you in the Rademacher expansion before. So, if you had forgotten, let me go several slides before. Sorry, where did I, here. So, our Rademacher expansion from the microscopic side also had this form, and now I am saying that each of these terms could be mapped to some ZC orbifold of ADS2. This is coming from a completely different computation from the microscopic side, using some modular properties of this counting function, and we would like to now reproduce it from the supergravity side. Okay. So, the general form of the answer, let us take for c equal to 1, will be e to the s renormalized times a measure that we still have not worked out. I mean, now I am going to tell you how to do it, then some one loop determinant, and then possible instanton corrections. Now, in fact, these instanton corrections can be put into here, and you can think of your S renormalized as some kind of renormalized action including all instantons. So, you can put it here or there. So, these are all the terms that we need to evaluate. Now, at the moment there is no off shell formalism with n equal to 4 or n equal to 8 with finite number of auxiliary fields. So, we will proceed in the n equal to 2 language. So, now in order to lift it to string theory, I am going to have to make some assumptions, and the assumptions are that I will just drop the various gravitini multiplets to go from n equal to 4 or n equal to 8 to n equal to 2. So, I will drop 6 gravitini multiplets, then I will drop the hyper multiplets, and then I will drop the d terms. And a partial justification for this is given by the fact that the black hole we will pick will not couple to any of the vector fields in this gravitini multiplets, and they do not contain any scalars. The hyper multiplets are known not to contribute to the black hole entropy, and but it is an important problem to actually understand these two things in a more covariant way in the some manifestly n equal to 8 formalism. And we will drop d terms assuming that they do not contribute to the wall entropy, because it is known that a large class of d terms do not contribute to the wall entropy in the recent paper of Dewitt and collaborators. But again, this needs to be shown, but I will just proceed with these assumptions, and we will get strikingly good agreement, as I will show you. So, therefore, one can look upon it as a post facto justification for these assumptions. Okay, so if you do that, if you use this n equal to 2 restriction, you drop everything except for the relevant vector fields, then you are left with only 8 vector fields. So, 7 vector multiplets, and they are described by pre-potential. Sorry, it does not even depend on this a hat. So, f of x, that are this pre-potential, depends in this very simple form x1 upon x0 CAB XA XB, where CAB is the intersection matrix for 6 2 cycles of T6, and then you will choose a simple charge configuration with 5 charges, Q0 D0 branes, Q2 D2 branes, etc. And we can just now plug in our formula and evaluate the renormalized action. It is useful to actually define some new variables which are duality invariant, and in this, which are, you sort of take out the charge dependence in some way and trade off these fields phi 0 and phi a for new variables, and in these new variables S renormalized take this particular form. It is a sum which looks like sigma plus z square upon 4 sigma plus a number of Gaussians. Now, to evaluate it further, we have to evaluate one loop determinants. It turns out, because we have abelian gauge theory, unlike in the gauge theory where you have non-abelian gauge theory, the quadratic fluctuation operator does not depend on the collective coordinate. So, the determinant factor just gives you some constant. The instantons in the n equal to 8 case are actually not there. So, therefore, in the n equal to 8 context, everything is really simple, and you only need to evaluate the induced measure, because you are sort of restricting yourself in some sub-manifold in the field space. But that you can do, because given the metric on the field manifold, you just look at the induced metric, and that is some procedure that you have to work out, and we do that, and you get a very simple answer for that induced metric, which is given by this in terms of the Kähler potential defined in terms of the pre-potentials. So, Fi are the first derivative of f with respect to x. So, we just calculate e to the minus k, which is given by xi f bar I minus x bar I Fi, imaginary part minus I, and then you calculate these things, calculate this Mij and calculate the determinant, and then you are done. When you do that, the final answer reduces to this, which is exactly the Bessel function I 7 by 2 pi square root of delta. So, you see that, so let me just show you some comparison now. For delta, now, so the, for example, in the Bekenstein-Hawking entropy, typically you took delta to be very large, but with this formula you should be able to take delta 3, 4, 5, so these are the values of delta 3, 4, 7, 8, 11, 12. The d of delta are integers, of course, 8, 12, 39, 56, 152, 208. W1 of lambda delta, which is the first term in this infinite expansion, you can see already approximates these integers rather well. Okay, you can basically guess what the integer should be just by looking at them. If you had instead computed the walled entropy, as was done say Bekenstein-Hawking entropy, then you would have done exponential of pi square root of delta, and you can see that differs from the integer. It's quite way off, completely way off. And this you could not have fixed. This is the walled entropy. So, this you could not have fixed by adding higher derivative terms in your effective action. And basically, now you might think that the area of the horizon goes as 4 pi square root of delta in Planck units. So, already at delta is equal to 12, this area would be quite large, and one might expect that the walled entropy should be a good approximation. But basically there are logarithmic corrections coming from integrations over massless fields, and log of delta is actually quite log of this number is quite comparable. So, you see here the need to really talk about quantum entropy rather than walled entropy, because if walled entropy was the answer, then you would not have gotten this beautiful agreement. And you can see that. So, of course, as these numbers go very large, we will sort of go into the Bekenstein-Hawking region and large charge region, and we can just use Cardy formula or something like that. So, but this is a substantial improvement over just using the Cardy formula, for example. Now, let me also point your attention to this very beautiful fact that if you expand this particular function for all these values 3, 4, 7, 8, 11, 12 that I wrote down, the Fourier coefficients are actually alternating in sign. And a priori, from the microscopic point of view, there is no reason, because this is some Jacobi form, and in general it could have had positive, negative, any kinds of numbers, and after all evaluating an index, you would think in the microscopic theory. So, there is no reason a priori, and there has been a lot of confusion in the past about the index, whether we are computing the index or the degeneracy, and it is clear from a physical point of view that Boltzmann never knew anything about index or topological string. So, entropy should always be compared with degeneracy, but in the ADS2 context, it turns out that the degeneracies actually can be argued to be equal to an index. And in fact, therefore, you can see that d of delta, which is minus 1 to the delta plus 1, is a positive integer. So, this is a positivity conjecture by Sen from the point of view of ADS2, and you can see that in fact this is the simplest example where you can just verify it. And I think now Samir and collaborators have are proving it in some other contexts. So, how does this positivity conjecture of Sen go? You take the near horizon ADS2 geometry, which has SU11 symmetry. If you have in addition 4 supersymmetries, the closure of the superalgebra requires that the near horizon symmetry must contain a supergroup SU112. Therefore, it must contain an SU2. So, this just follows from symmetries. Now, further, of course, just because it has so this is something that we are familiar with. We know that there are no supersymmetric black holes in 4 dimensions which are rotating, which break the SU2. But of course, this does not tell you necessarily that you are working in the microcanonic, it is not, does not tell you that J is equal to 0, because these are gravity arguments, and it could be that the chemical potential is 0. You do not know whether you are in the microcanonical ensemble or the canonical ensemble. But the ADS2 boundary conditions tell you that you must necessarily be in the microcanonical ensemble. This is something that I have not explained, but it is true, and therefore, putting these two facts, the symmetry argument and this together, it tells you that J is equal to 0, and therefore, an index trace minus 1 to the J is equal to trace 1, and this is quite strikingly true for this particular counting function. Okay, you might worry that what kind of fermionic boundary conditions we are putting. Are we having periodic boundary conditions or anti-periodic boundary conditions? But it turns out, because the gauge, we are doing a functional integral and the gauge field is fluctuating, it doesn't matter, and the fermions coupled to it, both periodic and anti-periodic boundary conditions are equivalent. The Kloosterman sum, as you saw, is a very complicated, interesting sum over number theory, number theoretic objects, and it would be very interesting. We have partial results and the right structure, but we haven't been able to really do it completely. To summarize, so I'm really putting in my time, and I don't want tired people in the conference to wait over time. So to summarize, localization of the functional integral in supergravity and string theory, we have shown that the full functional integral of supergravity coupled to vector fields in ADS2 localizes onto a submanifold of critical points of this functional S of Q, where Q is a specific supersymmetry that I talked about. We have obtained exact analytic expression for a family of non-trivial complex instantons as exact solutions which are completely universal and independent of the form of the physical action. In string theory, there are non-perturbative corrections from orbifolds as well as from brane instantons, and they have to be taken into account. So basically, if so far we have not actually completely gotten the Kloosterman sum, and that's an interesting open problem, and I think hopefully we will be able to do it in some simple examples at least. It looks like that the gravitational theory has all the ingredients to exactly reproduce this Rademacher expansion, and there is a lot more work needs to be done to first to understand this Kloosterman sum, and some of the assumptions like the dropping of d terms or hypermultiplets etc. have to be better justified. But here you can see that there is it's not it's a completely well defined problem that you can ask yourself, and there is an answer is yes or no. I mean, there is no, you don't have to make a conjecture, you can just check whether the d terms contribute or they don't contribute, or whether. So my guess is that actually even if you add hypermultiplets, the supersymmetry transformation laws of the vectors don't get modified. So therefore the instanton solutions that we have found will continue to exist. The only question is whether the action of the hypermultiplets will contribute to the S renormalized action, and that requires some kind of a non-renormalization theorem that we don't have at the moment. So it seems possible to compute finite size corrections to the entropy of BPS black holes in systematic way, going well beyond Bekenstein and Hawking, and such leading Bessel functions were partially derived in some earlier work with Denef, Kuehlen and Moore, but it relied on the unproven OSV conjecture, and at best it was an asymptotic expansion because there was no systematic way of determining the measure of the range of integration. Moreover, because the OSV conjecture applied to mixed ensemble, whereas here from an ADS2 perspective, the natural ensemble is the canonical microcanonical ensemble. So you really need to worry about a single integer d of lambda, which is the number of black holes corresponding to that particular ADS2 horizon. It was not clear how to incorporate the holomorphic anomaly systematically, these logarithmic terms that I talked about, but here you can see that they come by doing this procedure of functional integration over ADS2. So anyway, so these are, I think I have already talked about this. Yeah, so it's a microcanonical ensemble, and it gives you, and because we are doing it using localization, one obtains the exact Bessel function, because as I told you, our instanton solutions where this x goes away from the attractive values very far in the field space is an exact solution. We are not using semi-classical approximation. So therefore, it's not an asymptotic expansion, but really exact answer. So now this suggests some interesting connections between gravity and number theory. The Rademacher expansion is actually an exact expansion. It is very rapidly convergent, as you already saw from that table, but at no finite order can you assert the integrality of the sum, because as you saw, you got these nice numbers which are pretty much, I think this was done already by Ramanujan and Hardy, that you could estimate what the integer is, but you cannot really say that this is an integer, and at no finite order will you be able to say that this is an integer. But the nice thing about the Rademacher expansion is it sort of guarantees you that after doing this infinite sum you will get an integer, and therefore it's kind of tantalizing that a functional integral which you think is a very continuous object is able to reproduce an integer. It indicates some kind of an integral structure to quantum gravity. I think this is suspected from many, we know that how can quantum gravity be dual to SUN? There is an n there. So, but here is a sort of a manifestation of the same phenomena, but you can really get that integer out. And this would never be evident from the semi-classical Bekenstein-Hawking formula. Okay, so this I can skip. So, therefore, on a more philosophical note, our computation indicates that the quantum entropy is, in some sense, quantum gravity in the bulk is as fundamental as the boundary field theory with its own rules of computation. And therefore, unlike what has been suggested by some people, it looks more likely that it is an exact dual description rather than some coarse grained description of the boundary theory. It is worth exploring this duality further to maybe compute the correlation functions. And the fact that the bulk functional integral reproduces an integer, I think, is very interesting, and it's sort of the kind of thing that you require for information retrieval. That the fact that the bulk is able to see this quantization, well, after we do this Klustermann sum, maybe one can understand information retrieval. Maybe this is a kind of a first step towards understanding information retrieval. So, I think I will stop here, and yeah, maybe I was going to talk a bit about this mock modular story with n equal to 4, but maybe I will spare you the details. I will stop here.
So, basically all the expansion you've been talking about is in powers of inverse charges, right? That's your Rademacher expansion. And
so, the Rademacher expansion is actually an exact expansion,
yes,
it turns out.
But in, okay, exact function.
Yeah, so it's not an asymptotic. So, like for
I
example,
don't mean asymptotic, but I'm saying the power series is in powers of inverse charges.
no, it's in a square root of delta.
Yeah.
Yeah. So, when you expand it in a power series, yeah, it will be an inverse charges if you expand it as a power series.
Yes,
But
yes.
this is a function.
I understand.
Yes.
So my question is, but that this is done at fixed alpha prime, right? You fix alpha prime, you're always working at lowest order and alpha, I mean, how is alpha prime coming into this?
So, what we imagine is that we are keeping alpha prime in the game, and the massive string modes are, you just integrate them out to obtain some effective action for the massless switch, including the effect. Therefore, effectively you are including all the effects of the heavy string modes. But then you have to use some logic like the prepotentials of, because n equal to 8 does not get renormalized a lot, you can, and d terms don't contribute, then effectively then in the end the massive terms don't,
But some alpha prime corrections do contribute, right?
Yeah, so in this example they don't, but for example if you do n equal to 4 black holes, there are alpha prime corrections and they are quite important, and you can put them in and you can calculate.
But even the d terms are not expected to contribute?
So they don't seem to be. I mean, if you try to compare the microscopic answer with the microscopic answer, it doesn't look like that you need the d terms. But at the moment we don't have an a priori, there must be therefore, and there is a partial non-renormalization theorem due to Dewitt and company, but they have not really proven it for all d terms, and this is an open problem, and I don't.
And the f terms you're saying are just not there in n equals 8.
In n equal to 8, basically this is the only f term in this truncated theory. Yeah.
And in n equals 4 there are only finitely many?
Yeah, there are finitely many, basically because the topological partition function terminates at one loop in n equal to 4, because the K3 cross T2 has too many fermionic zero modes. Whereas on a general Calabi-Yau, you will get a topological string going to all genus, and in n equal to 8 it terminates at just the sphere. I mean, not.
So when you talk of non-perturbative, you use the word non-perturbative few times. You mean
It's non-perturbative in charges because we are
charges.
finite charges. So, for example,
possible non-perturbative effects in alpha prime?
so they are taken into account.
Taken into
They are taken in this n equal to 8 example. They are taken into account on both non-perturbative in string and non-perturbative in. And they are non-perturbative in this sense that you have exponential of pi square root of delta, but the next term in the Rademacher expansion is exponential of pi square root of delta divided by 2.
Yeah,
And
okay.
so on.
So these are the
it's non-perturbatively suppressed compared to the first one.
So these are the orbifold.
Yeah.
Other questions? Okay, so I think we should thank Atish for finishing the time.
And